Hello everybody, we are Zolin and Francesco and we are introducing our work for this course we title Completing Missing Sensor Modalities with Deep Learning. So let's introduce the task first. So the task is called Satellite Imagery Feature Detection and it consists in classifying areas of images taken from satellites as we can see here in the picture. So basically satellites will take a picture of an area of some land which will contain objects like building, roads and so on. And the goal is to first detect in the image this kind of objects. And secondly, we need to classify. And so usually we have a list of classes such as building, crops, road, and trees. And there will be also different kind of competition, for example, like the one organized on Kaggle by the STL last year, which had a prize of $100,000. And one specific property of this kind of task is that satellites have much more advanced imaging sensor than ordinary cameras, such as drones or smartphones or CCTV cameras. And one of the main aspects is that not only there are RGB channels, but also additional bands for specific frequency ranges. For example, in the case of the competition on Kaggle DSTL, beside three RGB bands, there will be one panchromatic band, so that goes on from this kind of range of frequencies, then 8 multispectral bands, covering each one a specific range of frequencies from 400 nanometers to 1040, and then 8 short waves bands. And here are some examples. This is one image from this dataset, and we can see on the top left the original image, RGB, so 3 channel, as most of images from ordinary sensors. Then on the top right, we see the panchromatic channel, and then multispectral red band, and finally shortwave first band. And then we can see that these 3 channels differ in brightness and also how blurry they are. And so here we identify a missing data problem, because we can assume that RGB ordinary sensors are relatively cheap, and also satellites companies charge more for the full band suite. This means that if you are interested in paying for having complete band data, then it will be kind of expensive. And also, there are some high-performance deep learning models which have already been trained on existing datasets on the complete spectrum band dataset. For example, the winner of the competition last year. So we raise here a research question. Can we use the full band existing models on dataset where some of the channels are completely missing, as in the figure below? So here we introduce our goal and also our method. So we want to design a deep learning model for reconstructing the missing bands from scratch. So very simple. So on the input will be simply a RGB image, which can be obtained for cheap price. And then there will be a deep learning model, like here in the illustrations, and the output will be a set of missing bands. For example, 17, as in the case of Kaggle competition. And the predicted bands can be plugged in any state-of-the-art pre-trained model, like for example UNet or the winners of the competition. So the training will consist in defining first some loss function. We came out with 2 choices. One is mean square error, will consist in comparing directly the output, the predicted bands output from our model with the ground truth. And the alternative is to use the structural similarity, which captures more high-level properties such as luminance, contrast, and structure details. Why we choose to try both metrics instead of only choosing one? Because the 2 metrics have different kind of behaviors. And for example, mean square error is extremely sensitive to variations in brightness and blur. So we can see in the examples the second image is darker than the first one. The structure similarity is very similar, but we see a very big gap in mean square error. And also in the case of a blurred image. And so we train using both metrics, and then later we analyze the differences.
Hello everyone, I'm Zolin. I'll be taking over from this portion onwards. So over here we describe some details about our experiments. So in this portion, so how we measure our performance is we basically have a baseline model which is based on the UNet architecture. In this baseline model is trained with all the channels, all the 20 channels that is available. And here's some details on the data processing. So what we do is we do the very standard zero mean and unit standard zero mean and unit standard deviation normalization. And another thing that we do is during the because the original image size is very big, is 3000 by 3000 pixel resolution. So since it cannot fit onto the GPU, we crop it into 512 by 512 patches. So another processing that we do is for the SSIM generation methods, which is where we take in the RGB images and then we predict the other 17 channels. We because SSIM is not sensitive to the absolute scales of the input and output range, so we first predict the channels to 0 and 1 range, and then we multiply by the channel's mean. And so the different channels standard deviations and means you can see in this table. So you can later, as we discuss, we will refer to this table, which we can see that the mean is actually different from typical images that you can see from the camera. So let's say for the RGB, you can see that the values, that mean is actually not 128, is much bigger than that. And then we even have channels that are almost 4000 range. So because of this high absolute value ranges, it caused some problems during our prediction, which we can see later. So we try a couple of different methods for filling in the missing channels. First is we try the naive baseline, which is we simply don't have any learnings and we fill in the rest of the, let's say, so in this case, in the first case, we fill the 17 channels with the RGB, with the R channels. And then in the second method, we fill it with the mean of RGBs, and in that method, we fill it with zeros. So, in these two cases, because in the typical subtraction by mean and division by standard deviation, we actually change. So we are actually dividing by the. So in the first case, we are dividing by the mean. We are subtracting by the mean of R channel and dividing by the standard deviation of R instead of the respective channel means to ensure that the data is still zero mean and unit standard deviation. And then we have two different methods which we propose, which is the SSIM based model and the MSE based model. And then we have another model which is our full original model. So here are the results. Our baseline model is actually very good. So this ranks about ranked 12 in the Kaggle leaderboard. So we are trying to. So our goal here is whether we can recover this performance without losing, while minimally losing when we only have RGB channels. So we can see that in the naive methods, the first three, the performance is actually not very good. But the surprising thing is the zero fill channels actually perform better than the R channel. So why is so? So initially we were quite surprised by this result, and then we investigate and then we list out such values such as standard deviation and mean, and we realize that the distributions is quite different for different channels. So the thing is, even if when we fill it with R channels and we divide by and we perform the normalization accordingly, our thesis is that it actually diverged a lot from the distribution of the original channel than the zero mean. So than the zero filled result. So that's why we think the zero fill result perform much better, because our not typical normalization for this R channel and average of RGB methods, basically kind of introduce artifacts in the channels. And then another one is the SSIM and MSE model. So the MSE models perform a lot better, which we will discuss the reasons later. And so our performance degradation is actually quite big, 44%. But compared to the baseline, we almost recover quite a bit. It's like we only lose 44% instead of losing like 80% of the accuracy. So here's some qualitative visualization of SSIM and MSE. So just note that the data is actually scaled based on the minimum and maximum value. This is why you are seeing that the SSIM is very dark here and the MSE is very bright here. So but if we actually scale by disregarding those outliers, they're actually kind of similar. But what we notice is SSIM will actually tend to capture the structural details much better, such as the blurriness, which MSE model is not able to do so. And because of this, our initial opinion was SSIM should perform better, but in the end, it turns out that MSE performs a lot better than SSIM. So because of this, we tried to perform some analysis, like why that may be the case. So what we realized is that the SSIM is actually not sensitive to the scale of the images. For instance, let's say you have two images, and then you multiply one image by some constant, then the SSIM of the remaining values will not change, in fact. So because of this, during the training, SSIM might get stuck in some random absolute value ranges, and yet it's still learning the structural similarity. But then the range that SSIM is predicting is very different from the range that the actual values are. So you can see that. So over here we try to check the predicted values main difference. So after convergence, so we calculate the difference with mean and difference with mass. And as you can see, the MSE is actually predicting the mean and mass of our original data distribution much better than SSIM. Like for instance, in the case of mass, the difference is actually quite big. It's like an order of magnitude more difference, or in fact 2 more orders of magnitude. Yeah. So we believe that because of this, the segmentation models are very sensitive to the input absolute value ranges. So regardless of how good SSIM is in emulating the structural details, since it is not able to emulate the absolute value ranges, the performance suffer a lot. So in conclusion, in this work, we have shown that it's possible to significantly recover the prediction ability of a CNN which is missing in high-end channel. So this case can be, even though the recovery is not very good, but we believe that this work is a beginning which we can hopefully obtain maybe 80 to 90% of the recovery accuracy. And then we propose an image regression model with 2 loss functions, MSE and SSIM. And we found that the deep models are very sensitive to the input value scales. And then because of this, MSE is more effective. Over here, we actually realized something. The MSE values, after it might be possible to train SSIM on the model that was initialized with MSE. So the thing about SSIM is you can think of SSIM as it's simply comparing the structural details regardless of the input ranges. So if the structural details are the same, it will actually never update the input range. So if the original input ranges are already fixed to a certain range, such as the result from MSE, then the result from SSIM might be improved further by initializing with MSE, pre-training with MSE. And another thing is, compared to our full band model, our model achieves 44%, only 44% degradation. Yeah, that'll be all.